All right. Last lecture before the exam. Everybody's ready for the exam next week?
What day is it again? Monday or Wednesday?
Monday. Well, it's Monday and Tuesday, or Monday and Wednesday.
Oh, it's a 2 day?
It's a 2 day.
It's still the day after my birthday.
Are you gonna
My
split it
birthday
up
is
like
not
chapters
changed.
1 through 3 on Monday and?
That's the way it works, yeah.
Sweet.
So, makes it a little bit easier, I guess, to study if you know.
Yeah.
You've got the day between to put extra work into the other one. Did everybody get the copy of the equation sheet that's sent out?
Yeah.
Okay. Anything that's not on the equation sheet, you're responsible for memorizing. Or it won't be, but I mean, simple things like, I don't know if stress equals F over A, sigma equals F over A. I don't know if that was on there, that kind of thing. Hopefully you should know. All right. So last time we talked about symmetrically loading a bar. Now we're going to use an unsymmetric bar. I don't know why it's unsymmetric rather than asymmetric, because it could, I suppose, be symmetric in the vertical axis, just not symmetric in the horizontal. Anyway, unsymmetric loading. So now, if you look at this picture that's sort of drawn on the overhead there, this is the x, z from the y-axis. So now it's clearly not symmetric about the y like we had last time. So the little element up here is experiencing a force. And it's the position of that element is z away from the y-axis and a height y away from the z-axis. And the element still has an area dA. So, but we're still applying a moment in the z direction, right? So you note the moment out there is still a pure z moment. We're trying to bend this bar upward, but now the bar just is asymmetric. Okay. So the moment about the y-axis, the moment about the y-axis contributed by this little element dA here, is going to equal z times d, oh, not dA, df. Right? Z is the distance away from the y-axis, so it's going to create a moment about the y-axis, df. Which we could write based on the direct derivation we had for force last time, is z sigma dA. And again, if we're going to get it to bend purely, and by purely I mean only in the direction of the applied moment. So in other words, we apply moment in the z, and we get a bend that is only in the z, then the moment about the y-axis must be 0. We see that? In other words, we sum these up, we can have no net moment about the y-axis if we were to get it to bend purely about the z. Because if there's some moment about the y, it's not going to bend like this, it's going to bend off in some wonky way, even when we apply a direct y moment, or z moment. Okay? So we have to get that piece to equal 0. Actually, the integration of those has to equal 0. Not that. So once I put my, therefore, is equal to the integral of z sigma dA, and that's got to equal 0 over the area. So, do the substitutions that we did last time, same idea from our earlier analysis. Sigma was equal to what? Anybody remember?
C over rho.
Remember that? Okay. So it's some fraction of the maximum. So we end up with the integral, the area integral of z times negative y over c sigma max dA. The sigma max and c come out because they're constant. And we're left with integral of zy dA. Anybody recognize the integral of zy dA?
That is the centroid.
That is not the centroid.
What?
IZY.
ZY.
IZY, that is the product of inertia. The other piece is in there. Minus sigma max over c times I zy, the product of inertia in the zy plane. Remember that? Okay. And again, that's got to be equal to 0 in order to get pure bending. Is sigma max going to equal 0? No, not unless we have no moment. Is c going to equal 0? Not unless we have no bar. So IZY must be equal to 0. So in order to get pure bending for an unsymmetric bar, we must have a product of inertia, IZY, equal to 0. Remember the calculation we did for IZY last time? IZ minus IY divided by 2, so on and so forth, or plus y, and then, anyway, you have the equation. But there's one additional equation that we talked about on, what was that, Monday? I think it was Monday. And that was that the tangent of 2 theta p, anybody remember what theta p was? In that derivation from Monday. So when we talked on Monday, we talked about the moments of inertia, right? And said that there's this moment of inertia, IZ, there's a moment of inertia, IY, and then there's a product of inertia, IZY. And we then did an axis rotation to a Z prime, Y prime axes. You guys remember that? And there I didn't derive it, but I kind of just gave you the final solutions, and I said that there is a particular angle at which you can rotate the coordinate system so as to have a minimum and maximum moment of inertia. So when we flip the phone, remember flipping the phone? So there's a minimum and maximum moment of inertia for the body. And you rotate the axes by theta p. And when you rotate them by theta p, you get to the point where the y prime and z prime in this case axes are the maximum and minimum moments of inertia. Okay. Just going to take my word for it at this point. Sure? No? You have no recollection of this discussion at all? You know everything is on video. I can go back and prove it. Okay, so if we rotate, in other words, this thing wants to flip about this direction or that direction, if you will, in using the phone analogy. It would most readily rotate about this direction or that direction because those are the minimum and maximum moments of inertia. Okay? So we got to figure out, so the theta p was about figuring out what angle we needed to rotate our coordinate system to get to that minimum and maximum orientation. And the way we calculated that was minus 2 I zy over I y minus I z. That was the calculation to find theta p. But if we just said that in order to get pure bending, IZY must be equal to 0, then that says that theta p, or that the tangent of 2 theta p, must also be equal to 0. When is the tangent equal to 0? What values of theta give the tangent equal 0? 0 degrees, that's one of them. Well, 90 for theta p, right? because tangent of 180 is 0, right? So theta p must either be, for this configuration to work, theta p is equal to either 0 or 90, or 180, 270, whatever. You know, it's an integer multiple of 90. So what does that mean? That means that in order to get this thing to bend purely, we must already be, because when theta p equals 0, right, that means we don't have to rotate at all. We must already be oriented along one of the principal axes. In other words, the moment of inertia about the z-axis and the moment of inertia about the y-axis already are the max and min moments of inertia for this beam. So if I have an unsymmetric beam and I bend it purely, am I able to bend it purely, meaning apply a moment in the y and it bends purely in the y? That means that I must already be aligned with one of the principal axes, either the major or minor moment of inertia,
So how,
max or min.
how does it know that we're already aligned, I guess?
So it doesn't know.
Well, I guess like,
It's not a sentient being.
but, do you know what I'm saying though, like?
So that's because,
Where in the math did it show, like?
because look at this. In order to get it to be 0,
Uh-huh.
that means we gotta have as much pushed that way as we have pushed this way, acting on that beam because of the bend. Right, so we're bending it, we're getting compression here at the top.
Mhm.
We've got just as much compression, force acting on that side, which would cause the rotation one way, as we have force acting on the other side of the y-axis, so it's pushing down. So even though it's not symmetric, the total integration of the force acting on this side is equal, or the total integration of the moment created by the force acting on this side, is equal to the total integration of the moment acting on the other side.
Okay.
So that it doesn't try to twist. Okay? And this is again why, if I'm at the major or minor axes, I can get this thing to flip fine. Because my moment is not inducing a bend, or in this case, a dynamic rotation, in any other direction. I'm getting pure rotation here, I'm getting pure rotation, well, here. I'm getting pure, sorry, I should step on the camera. I'm getting pure rotation here, and I'm getting pure rotation there. Because those are the major and minor moments of inertia, the maximum and minimum moments of inertia. And if I try to do it in between, I end up creating a moment about each of the others because of this unsymmetric rotation of my object. Okay, so it's not exactly the same. This is a dynamics rotational thing. This is a bending thing, but it's the same idea. Yeah, Kyle.
So is there a way we can look at that phone and tell which is the major and which is the minor axis, or minor axis of rotation, bending moment?
Well, actually, it's the moment of inertia. that we're
Moment of
concerned
inertia.
about, right? So this is the minor moment of inertia because I have the mass is closest to the center of rotation. Okay, so I can't do it with one hand. Right, in this configuration.
So that's the minor?
This is the smallest moment of inertia.
Okay,
This is the minimum moment of inertia.
okay.
Because this is the point where the mass is the closest to the center of rotation. Here,
Maximum inertia?
the mass is the furthest from the
Right.
center of rotation.
Right.
In between, it's in between, and that's why we don't get good stable rotation there.
Okay.
Okay. There can only be one max and one min. Anything else creates instability. Okay, so if it's equal to 0, then we're at a principal axis. If it's not equal to 0, then we're not at a principal axis, and we'd have to move.
Okay. Got it. Something just clicked, sorry.
Okay,
So we don't, okay, I got it.
okay,
Yeah, I got it.
all right.
I see what you were gonna say, because it helps the rest of us understand too.
Well, we have to still solve to make sure that it's equal to 0.
Right, or if, yeah, if we know,
Yeah,
if
we have to
we
say-
apply a moment and it bends, then we know we're already there.
Yeah.
Right.
I was wondering how we already knew it equals 0.
Because I started off by saying, if we get pure bending.
I missed the F part.
Okay, all right. So, and for what it's worth, if there is symmetry, the principal axes will always be perpendicular and parallel to the axis of symmetry. Because if I have symmetry, then along y, then that means I have an equal moment on either side of y. Therefore, the sum of the moments equals 0 about y, therefore I'm at the principal axis. Okay? So if I've got principal axes, they're always going to be lined up perpendicular to or parallel with the line of symmetry. Okay, if there are two lines of symmetry, as you would have with a circle or a square would probably be a better one because a circle would have, would be axisymmetric. A square has two lines of symmetry, right? They're both there, so they're going to be equal. With a rectangle, you have two perpendicular lines of symmetry, but one's the major and one's the minor. One's the max and one's the min. Okay. So what happens when it's not? Right? So now we're going to say, okay, let's say it's not equal to 0. What do we do? So here's the process for if the applied moment is not along a principal axis. What's not? X? No, that's all. What's X? No. What's the logical symbol for not?
NOT.
Oh, fine.
Oh, you sass.
Fine. Okay, so if it's not, what do we do? First step. Separate the applied moment into a piece perpendicular to and a piece parallel to the principal axes. So in other words, whichever way you look at it. If you're parallel to one of the principal axes, then the other one is automatically perpendicular to the principal axis. Right? So I'm being redundant there. If one of them is parallel, then the other component is perpendicular by definition. So in this case, let's assume this is not symmetrical, right? If we had an axis of symmetry that was, up here somewhere, right? And we're applying this moment, this z moment. Right, that's our applied moment. We want to break it into a component along the axis of symmetry and a component then perpendicular to that axis of symmetry. You can see what I'm drawing up there? So I'm applying the z moment, I'm bending this beam, but the principal axis is not, the principal axes are here. Right? Those are the principal axes. So I take a component, figure out what's the component of the applied moment along that principal axis, and the component along this principal axis. Okay, so I call this piece M y prime, and this piece M z prime. Of course, what I applied originally was just mz along the z axis. Where y prime and z prime are the principal axes. Okay, everybody got that? Clayton, still?
Maybe it's just the picture that I'm.
Three-dimensional drawings.
Yeah, I'm just, so both of those components will take care of the entire moment.
Right, so there's an angle in here, and so I'm taking m cosine of that angle and m sine of that angle, we break it into these two components.
Yeah, I'm just I'm trying to
So
visualize through that.
This is theta p here. So this is theta p. So the z component, the z prime component would be m cosine theta p, and the y prime would be m sine theta.
Okay.
Okay, so you separate into those two. Then you've got sigma z is equal to minus the moment about the z-axis times y divided by I in the z-axis. We talked about that last time. Right, we derived that expression last time. And similarly, the sigma caused by, the stress caused by the y moment is my times z divided by IY. So that the total stress at any point on this, in the cross section is going to be the sum of those two. Negative mzy over iz plus myz over iy. And you notice that the first one is negative and the second one is positive. That's derived from the right-hand rule convention that we use for defining our axes. So if you look here, any component of anything that pushes in this region, right here, right? Any force that acts in this region is going to create a positive moment in the y-axis. Right? So if I'm pushing on there, I have compression there, then I'm going to get a force pushing there, then I get a positive moment on the y-axis. Right? So a positive z gives rise to a positive moment. But about the z-axis, let's see here, is that right? This is that, that's that. Oh, but that, yeah, no, I take that back. So it's a positive, yeah, so that's going to create a positive y, but it's going to be a negative z. See what I'm saying? In other words, I have a negative z out here. Any negative z is going to create a positive y. But any positive value of y is going to create a positive z.
What axes are we talking
Y prime or x prime, the primes or the non-primes, it doesn't matter. Just look at it in terms of the non-primes because they're a little bit clearer to see on the board. Anything that's going to cause a positive moment in the y-axis is going to involve a compressive force on the z side. But it's a negative z. So I have a negative force, because it's compressive, and a negative z, those two combine to make a positive moment in the y. So the moment in the y is positive. That term is positive. If, on the other hand, I want to talk about the moment about the z-axis, or the z moment, I'm going to have a compressive force, a negative stress, but a positive y. Right, so I have a negative sigma and a positive y creating a positive moment. So for that term, I have to add an extra minus sign in order to get the signs to work out correctly. Okay, so the minus sign is just about getting the right-hand rule, conventional orientation of the axes to work. So essentially what we're saying is you have superposition. If you have a moment that's not along the principal axes, then you got to find where the principal axes are. Break that moment down into those two pieces. And then sum the stress caused by each of those moments to get a total stress. Okay? I don't know if we're going to get to do that today or not, but at least you've got the general idea. Okay. So, the neutral axis then of my beam, remember the neutral axis we talked about last time? We want to find where the neutral axis is. What is the stress going to be on the neutral axis? Or zero. If you ate lunch on time, you're just too dedicated a student. You had to put off lunch because class was more important. Is that what you're telling me? Sure, okay. All right, so sigma 0, right? On the neutral axis, sigma 0. So we set this thing equal to 0, and we find out that on the neutral axis, myz over iy is equal to mzy over iz. Right? These two have to be equal terms because the total stress is 0 on that axis. So therefore, if I rearrange this, y is equal to my over mz times iz over over IY times Z. So there's an equation for a line relating Y and Z that defines the neutral axis. Now, going back to your question earlier about how do you break that, was it you guys, about MY and MZ, right? What's MY? What did we say MY was?
It's like,
Zero.
No, I mean in this picture.
Oh,
Like
Cosine.
cosine,
Is it cosine or sine?
sine.
It's sine. Right, so MY is M cosine theta. I'm sorry, I just said sine. I wrote the wrong thing. M sine theta. What's MZ? M cosine theta. IZ over IY MZ. Well, the m's cancel out. The sine theta over cosine theta is tangent theta. Okay. So if I want to find the orientation of the neutral axis, I have better pictures down here. Yeah, there it is. That's the, you can kind of see there the better components on the second figure. See how you take that moment in the upper left corner, break it into components along the z and y axes, right? And then each of those gives rise to a stress distribution. But if I come in here and say, well, where's my neutral axis? My neutral axis, yeah, that's okay. My neutral axis is in here someplace. At some angle alpha. Right, so the neutral axis is some angle alpha relative to the y-axis to begin with. So y over z is going to be equal to the tangent of alpha. Right, along any coordinate along that point, y over z equals the tangent of alpha. But according to my rule, or my thing up here, that's going to be equal to the tangent of theta, iz over iy. So I can find the neutral axis if I know the theta p, and this is theta p. I'm not going to put the subscripts on there. The angle of the principal axis. The angle to the principal axis. So tangent alpha, the neutral axis, is related to the position of the principal axis. And if iz equals iy, if iz and iy are equal, then theta and alpha are the same. So in a case like a square cross-section, where the moment of inertia about the z and about both principal axes are the same, then the neutral axis will be aligned with the principal axis. Okay? So it's a lot of stuff, I realize. Actually, yeah, I take that back. Alpha is fine with respect to the z-axis, not the y-axis. Anyway, look at your book. Better picture in your book.
So you said we have that equation of the line, the z or y equals m sine p over cosine. Can we just graph that line on our YZ axis?
Yeah, I'm just trying to get you to the point where it's easier to, to an expression to that line. So in other words, this expression here, is this the one you're talking about? So this expression here, you can plot that out.
And you just plot, okay.
You just plot that out if you wanted to, right?
Yeah.
But I'm just saying that it's easier to think in terms of where is that angle, where is that line located, and then I'll just draw the straight line.
Mhm.
So instead of plotting it out, I just solve for the tangent of alpha, and then plot that out. Okay. I'm trying to find, let's see if there's a better picture that better captures alpha. Yeah. Oh no, it's on that big, it's on there. You just can't see it very well. It's up here. My pointer.
Is that the A, or no?
That's the alpha right there, between the neutral axis and the z-axis. So again, on here, I said it's I defined it with respect to y instead of with respect to z. That's alpha. Okay, that's a lot of heady stuff. If you have any questions, you want to start trying to apply it. You have a question?
So are we only going to be dealing within, we're not going to be dealing with the moment that's like in with three-dimensional rotation?
So you could, but you would define your system based on the applied moment. Right, so you know, if I have a beam, so coming out of the wall, and I twist it in some random direction, well, I'm just going to say, okay, well, that's my y-axis, so that I'm creating a z moment, and then I do the principal axis, and I rotate it over to the new principal axis. Okay, so whatever the moment is, I'm going to break it into components along and perpendicular to the principal axis in order to get the unsymmetrical. Or I'm going to hopefully apply the moment along an axis of symmetry, which is a principal axis, and then I'm done.
How much work would it add if we added a x component to the moment, say, that moment up there?
A twist. So an x component to that moment would be a twist.
Would be a twist, oh yeah.
And so then we would just go back and analyze that piece using the twist approach that we talked about before, the torsion. Right? You get a twist out of the x component, you get bending out of the y and z components. Okay, so now we've got all, basically, once we've completed this, we've now covered all the possible deformations. A normal force along the length, shear forces, which can be applied in y or z, right, which we've already talked about. Torsion, which is a twist on the x, or rotation on the x, and then bending in the y and z. So we've covered all the possible bases. Okay? All right, yeah.
So if we had a twist on this too, and then we went separately and calculated the twist, we would just add our twist stress into we just add it into our overall stress, right? To get our
Right, so there would be, yeah, but what kind of a stress does a twist stress create?
Shear.
Shear stress.
Okay.
So a twist will create a shear stress, a bend creates a normal stress.
Okay.
Just like a normal force creates a normal stress, and a shear force creates a shear stress.
Does a bend create any shear stress?
A bend does not create shear stress. Well, okay, to a first approximation it doesn't. Once you start really deforming the bar, then yes, it does create a shear stress. But as long as the bar remains essentially straight, so you're applying a stress, but it's still essentially straight, then there's effectively no shear stress. It's just a tensile stress.
Yeah.
Okay. Anyway, yeah, okay. And generally, yeah, even when you combine them, there's an interaction between shear stress, which creates a, normal stress, which creates a Poisson contraction or expansion. Remember Poisson's ratio? If I squeeze a piece of rubber like this, it gets bigger like this, right? So there's a strain in the lateral dimension when I squish in the longitudinal direction, or if I pull in longitudinal, there's a strain this way, opposite, right? That strain creates a stress in the other direction as well. So even though I'm pulling on it, I'm only applying a normal stress, there's still a Poisson induced stress in the lateral strain in the material. So it's still all interactive, and it really becomes a big there's basically a 6x6 matrix that describes the total response of the material. But we don't want to get into that now. That's an upper level course. Okay. All right. Let's do 6108. If the wood used for the T-beam has an allowable tensile and compressive stress, as shown, 4 and 6 megapascals respectively, determine the maximum allowable internal moment that can be applied to the beam. And they've given us a direction for the beam, or for the moment rather. So, what shall we do?
Free body diagram of the face.
Free body diagram of the face. See how he's picking it up now? He's not just giving me the free body diagram, but he's specifying the object. All right, of the face, nice and big. There's the face, sort of. I probably ought to draw it again because symmetry matters now. Okay, close enough. All right, what do you want me to draw on there?
That moment that I have no clue which direction it is going.
Okay, so first of all, we're going to find the centroid about which they're applying this moment. It appears to be, they have not specified the location of the centroid. This dimension is 50 millimeters. This dimension is 200 millimeters. And this is 50 millimeters, and the whole thing millimeters, 100 millimeters. Okay. I can say, yep. Okay, so they've defined the centroid here, but they haven't told us where it is. Right? They're talking about acting with respect to the centroid, presumably, but they haven't defined the location of the centroid. And then they've applied a moment, which is defined in the plane of the board. So the applied moment is coming up here at an angle of 60 degrees. Okay? So, is the moment, the applied moment, I'm going to keep that, along an axis, a principal axis? Yes or no? We
Can
have
I ask a quick question to visualize the moment? How would you apply a moment?
I would take it and I would twist it like this. And so
So
my
you're
thumb
twisting
points
it.
along the moment.
Yeah, so like
And
you're
I'm
twisting.
twisting it. I'm taking this beam and twisting, trying to bend it. I'm not twisting it. Sorry, I shouldn't say twist. I'm bending it in this direction.
Okay, got it.
Got it? Okay.
Yes, it is one.
I'm always bending it perpendicular to the moment, because the right-hand rule thing is thumb's always perpendicular. Okay, so what do I do?
This would be along the principal axis, right?
Is it? That's what I'm asking. Is it along the principal axis? What had I written
If it's
right here?
symmetric.
Principal axis perpendicular and parallel to axis of symmetry.
We can't read that from here, but that's.
It's written in your notes. I'm sure it's written in your notes. Let me come look, Colin. See if it's written in your notes. Not so much. We got unsymmetric and a kidney bean. All right. Axis of symmetry. So, is it along an axis of? Is there an axis of symmetry? Is there an axis of symmetry?
Right
Yes.
in the middle.
So he's doing this. Either he's blessing me or he's saying that there is an axis of symmetry up the middle. Okay. There's an axis of symmetry up the middle. Is my applied moment along an axis of symmetry? Along principal direction? No, it is not.
Oh, yeah, okay. Yes. No, it's not.
Too much violence in the football field, I think.
I swear I'm getting dumber.
Okay. Anyway, so it is not lined up along the axis of symmetry, which is the principal axis. So, what are we going to do? We're going to split it apart into two components. We're going gonna split it into a component here. We have an my component. And a component here, mz. Okay? What is each of those? My equals what?
Sine 60.
M sine of 60 and mz,
And cosine 60.
m cosine 60. And the applied moment m is what we're trying to find, right? Yes, we're trying to find m. Applied moment m. Okay? Now what? What's the limiting factor here? The stresses, right? The sigma. We know that we have a maximum sigma. Sigma allowed in tension is 4 megapascal, and the sigma allowed in compression is 6 megapascal. That's our limitation. So somehow we have to express a relationship between the applied moment and the stress. Do we have such a relationship we can find? What is it?
So the moment in the y direction would be sigma, negative sigma max over c.
Okay, that's not what I'm looking for. Go in the other direction. I'm saying, oh, I think I see what you're saying. Okay, that's fine. That's fine. I was expressing it. I want to find the total sigma. I want to find the total sigma. I want to find the relationship between sigma and the moments, right? The sigma, total sigma is minus, remember I had this written down here someplace.
Minus mzy over iz.
There it is.
Plus myz over iy.
That relationship, right? I've got my mg and my my, right? So I can plug them in there and solve for m in terms of sigma. Right? So if I wanted to, I would say, okay, mz is m cosine 60 y over iz plus m, minus that, plus m sine 60 z over iy. What value of y and z would I use? Hmm? The maximums. Right, so the z that I'm going to care about is going to be what?
We don't know the location of our,
No, yeah, so it's going to be 100 millimeters. Right? The z, the maximum z is going to occur out here.
yeah.
Right? So my z here is going to be 100, or well, make it 0.1 meters. What about my y?
How do we, since we don't know the location of our origin, how do we know?
We got to find our origin. Right? We have to find the centroid so that we can measure our y value relative to that centroid position. So how do we find the centroid? You're not going to get very far. How do we find the centroid?
Centroid of y would be the integral of y dA over the integral of dA.
Okay, well that's true. integrating a t is gonna be kinda hard. So what better solution do we have?
We split it up.
We split it up. We can say that that's also
Look it up.
the sum, we can look it up. T probably not.
So I mean, we can split it up and look it up if it wasn't this really simple shape.
Oh, okay.
We didn't already know the answer yet.
So we can do that. Where y tilde is the centroid of each subsection, sub-piece. Okay. So that's going to be y at the top, y bar at the top times the area at the top, plus y of the, what's the word?
Bottom.
Yeah, that's not what I'm looking for, but okay. There's an actual word for the spine. Bottom, all over the total area. Right. Does that make sense? Okay. So what's y at the top?
And that's for our centroid?
That's to find our centroid. That gives us y bar. Y at the top is 25. What's the area at the top?
5,000.
Or 1,000. 50 times 200.
Oh, 200, not
200 or 100?
10,000. That'd be 10,000. What's y at the bottom?
100.
So here's y at the top, or y tilde at the top. Where's y tilde at the bottom?
100.
Nope.
Well, 100 from,
Where is it? You gotta use the same coordinate system.
no, 125.
So.
Oh, no. What word is this?
I don't know, pick one. You said that was 25, I assume you had a coordinate system.
100 from the bottom.
What?
100 from the bottom.
No, 100 from, 150
You
from
said
the
this
top.
was 25, you made this 0.
150 from the top.
So it's 150 from the top. You see what we're talking about?
Or 100 from the bottom.
But you didn't give it 25 if it's from the bottom. Then this one has to become 225 then.
Alright.
It's used the same point of reference for both of them.
Don't mess with it.
So 150 times the area of the bottom. What's the area of the bottom? The same 10,000. They're both 2x4s. Divided by 20,000 equals. Oh crap. They converted everything to meters. All right. So it's 87.5. 87.5 millimeters. Good?
Yeah.
All right. Now we know where y bar is. Now what do? So now we know that y here, this, is equal to, well, relative to the bottom, I guess, it would be 250 minus 87.5. Right, because I said that one was 0.1 in from the left, right? So oh no, I said the maximum was the 0.1. Okay, so now the y maximum is going to be 87.5 in one case, right? Or MC here is going to be 87.5, right? It's going to be the top up there, but it's going to be 250 minus, or yeah, 250 minus 87.5. 100 and whatever it is. All right, let's look in here. It's oh, for crying out loud. 162.5. Is that right? Yeah, 250. Right. At the bottom. Which one of those two are we going to use? What's that?
Wait, why did you subtract it from the?
So this is, I'm measuring from the bottom up, is 162.5. So in other words, this distance here is 162.5. This distance here is 87.5. So my point is, we're using the maximum y value, right, to find our maximum moment. So I found this one and this one. Which one am I going to use? No?
So we have to solve for compression and tension?
So, it wants the maximum allowable external moment, which means that the larger Y will probably break before the smaller, right?
So, which one, so let's go back to Blake's point. Which one is in tension, which one's in compression?
Bottom one's in tension.
So the bottom one's in tension,
Mm-hmm.
the top one's in compression.
Yeah.
But we don't know what the effects, the relative effects of these two pieces are. So we can't automatically say, oh, it's going to fail in tension first.
Gotcha.
I'm saying we don't know the effects of the moment and the inertias to be able to say which one's going to be compressing and which one is tensile. So one time we're going to use 87.5 when we're doing the compression analysis, because if this is my moment, that corner's in compression. That's in compression, then this corner is the one in tension. Right? So my Y is going to be that. And then when I do that second corner in compression, my Z is going to be 0.025 meters to the second. Does that make sense? Because the Z is only 25 millimeters away from the centroid in tension. The tensile Z is only 25 millimeters away.
What about the other end of the T though?
This one here?
Yeah.
So, I mean, I guess you could,
Because aren't we breaking them up into components, or we're just considering, kind of like just considering the X moment and just considering the Y moment?
no, we're considering the total, X and Y. But we know that that corner is in compression, and this corner is in tension. I'm just trying to see if they even bothered with the other one. No, they did not bother with the other one. Okay. So, just by inspection, you can see that this is further from the line of it, further from the moment. This is further from the axis of rotation than this is. If you're confused, if you're not sure, then you try both points. Right? If it's unsure, you don't know whether they're the same, which one's going to get the greater tension, then you can try both points. But you should be able to, quantitatively determine that this one is closer than this one is.
Yeah.
And visually, I can just, you can just sort of tell, looking at the picture, oh yeah, the bottom corner is in bigger danger than the top, than this corner. Part of that is also knowing the neutral axis. We have to find we'd have to really know the neutral axis to find out for sure what direction it's going to rotate. Because it's the position relative to the neutral axis that matters. Right? So we don't necessarily know that the neutral axis is along this line. If we really wanted to find it quantitatively, we'd have to go in, find the neutral axis, the tangent alpha equals tangent theta p, ratio of the moments of inertia, find out where that neutral axis is, and then find out which point is furthest from the neutral axis. Because you always know the point furthest from the neutral axis is the one that's going to have the greatest stress. Okay? So you can go in and do that quantitatively. But to do so, when you kind of can tell that this is going to be the danger corner, you don't have to worry about it. It's just if it's really close together, you're like, well, maybe it's going to be more difficult. I can't really tell for sure, then you go in and try it. Okay? But there's not a neutral axis that can go through that centroid. It's not. The bottom line is not going to be further away. Right? The distance from here to here is greater than the distance from here to here. All right.
Okay, just to finish up that problem, we would get say we got the moment of inertia for.
So you have to calculate. Then you have to go back and calculate the total moment of inertia.
Okay, so that gives us the total stress, but is it just we add those two, the tensile and compression?
Right. You add. Well, they're not necessarily tensile and compression.
Yeah.
So you add these two together. You add these coordinates. Right.
So I guess my thing is, so we know that the m cosine y is the y portion of our stress, right?
The m, the cosine 60.
60 yes.
is the Z component.
Or
of
Z
the motion.
component, yeah.
Of the moment, yeah.
And Z is,
That's this one.
yeah,
So that's
okay.
the piece that's bending it this way.
Yeah, and then we know the other
So
one.
this is definitely tensile, most tensile for that piece.
Yeah,
Right?
and then we know the other one is
The
on.
other one is this way. And in that one, this one creates the most tension. Right?
Yeah,
So for this one, you'd see the greatest tension here. For this one, you'd see the greatest tension. For this one, you'd see the greatest tension here. But it's the combination of the two that matters, not just the individual ones. So you don't ever get, you can't combine the tension created here for one with the tension created here for another. We're trying to find the tension at an individual point.
so it's the
So it's
biggest.
either this point, and we look at both of them at this point, or at this point, and we look at both of them at that point.
Okay, so we look at the largest resultant away from our set. Okay, and then use the coordinates for that point.
Right.
Okay, okay, that
The
makes.
piece that's going to get the most tension, the piece that's
That
the
makes
furthest
more
away
sense.
from axis of rotation.
So I understand that side. Now, moving over to the left side of this, this equation, over on the other side equals.
That's just
So,
sigma.
that's just sigma, is that just,
So
is
we'll
that
find,
both of them or just one, or?
that's just sigma in general.
Okay.
So we'll plug in the top set of coordinates and find the compressive stress.
Okay.
And then we'll plug in the bottom set of coordinates, or vice
Oh,
versa.
okay,
Well, anyway, we'll
Yeah.
plug in one set and find the compressive one.
and then whichever end is the most, and that's our.
So you'll find, right, so you'll find an M given, well, no, you'll plug in the sigma and find the M that gives me that sigma. So in other words, this set of coordinates, right, for compression, here, right, up in that corner. So I use the first set of coordinates and know that that's going to equal 6 megapascal. And solve for what M is going to create that. And then I
you
use
turn around.
bottom set of coordinates, plug in 4 megapascal, and find out what M is going to create that tension.
Okay, then we take the smallest end.
And then we take the smaller end,
Okay.
it's going to be
Yeah,
the early.
that makes sense. I wasn't couldn't make that.
All right. Have a nice weekend, gentlemen.
Yeah, you too.
Hey, Blake,
Yeah.
your book.
Leave my books in.
Classic.